Welcome back to the deep dive. Today we are doing something a little different.
Little bit.
Usually we look at the output of technology, the gadgets, the apps, the societal shifts that happen when a new tool just lands in our laps. But today we are cracking open the black box.
Yeah, we're really going under the hood.
We are looking at the engine itself.
And it is a fascinating, sometimes messy, but just an incredibly powerful engine.
We are talking about machine learning. Now, I know what you were thinking. You're probably thinking, okay, I'm not a math person. I really don't want to lecture on calculus, and I certainly don't want to hear about vectors.
Right.
And I promise you this isn't that. We have gone through this massive stack of technical lectures, research notes, and coding workshops, and we've distilled it down to something else entirely.
It's really a story. It's a story about decision making. I mean, it's about how we teach a pile of silicon and metal to understand the world and maybe more importantly, to predict the future.
Exactly. It's the story of how we teach a computer to learn from experience. And we are going to take a very specific journey today. We're going to start with the absolute simplest concept. I'm talking drawing a line on a piece of paper.
The very beginning.
And then we are going to watch that concept evolve step by step into these complex logic trees, and finally into these massive forests of algorithms that can, diagnose diseases or trade stocks better than humans can.
It's an evolution. It's a real journey from utter simplicity to what we call the wisdom of crowds.
So if you have ever wondered how Netflix knows exactly what you want to watch next, or how a self-driving car sees a pedestrian and decides to brake, this is the primer.
This is it.
We're going to cover linear regression, decision trees, the deadly trap of overfitting, and the magic of what are called ensemble methods.
And we're going to spend some time on why garbage is the enemy of all of it. Because if you feed the machine junk, it just gives you junk back.
Right. Garbage in, garbage out, the classic phrase. But let's start at the beginning. The hook. The whole idea of prediction. Because really, that's what this is all about, right?
Fundamentally, yes. Machine learning is just a fancy, kind of intimidating term for using the past to predict the future.
Okay.
It's taking historical data and finding the hidden rules, the patterns that govern it.
So let's play a game, a very simple one, just to get our brains in the right mode. If I give you the numbers 1, 3, 5, 7,
Okay.
I ask you, what comes next?
Yeah, 9.
Okay, easy. And the one after that?
11.
Now stop for a second. How did you do that? You didn't pull out a calculator. You didn't, write a formal mathematical proof. Your brain just knew.
My brain recognized a pattern. That's all it is.
Yeah.
It saw that for every step forward in the sequence, the value increased by 2. It's a sequence of odd numbers.
But subconsciously, what did your brain actually find?
It found the function. Subconsciously, it found the rule is 2 times x plus 1.
You found the function. That is the key phrase for this whole deep dive. In traditional programming, the old way of doing things, we act like gods. We give the computer the rules. We say, computer, take this number, multiply it by 2, add 1, and then you tell me the answer.
Right. It was always input plus the rule equals the output. That's how we built software for, 50 years?
Exactly. But machine learning flips that on its head. In machine learning, we give the computer the input, the 1, 3, 5, and we give it the output, the answer key. And we say, computer, you figure out the rule. You tell me how I got from A to B.
That is the perfect definition. It really is. It is the automated discovery of the function. Instead of programming the logic, we program the machine to find the logic. And the simplest version of this, the absolute hello world of machine learning, is linear regression.
Linear regression. Okay. It sounds intimidating, like something I definitely failed in high school, but it's actually incredibly intuitive. The source material uses the example of house prices, which I think everyone can relate to.
It's a classic example, and for good reason. Imagine a graph. On the bottom, the x-axis, you have the size of a house in square feet.
Okay.
And on the side, the y-axis, you have the price of that house.
And we have data. We have a spreadsheet of 1,000 houses that were sold last year in a specific city. So we have the size and the price for each one.
So you plot them. You put a dot on the graph for every single house. A big house with a high price, that dot goes way up and to the right. A small house, cheap price, that dot is down and to the left.
But here's the reality of real estate and really reality in general. It's messy. You might have a huge house that's falling apart and sells for cheap, or you might have a tiny little condo in a super trendy neighborhood that costs a fortune.
Exactly.
So when you plot all these dots, you don't get a perfect, beautiful straight line like you do in geometry class. You get a cloud.
A scatter plot, that's what we call it. It looks sort of like a swarm of bees moving generally upward and to the right. The trend is clearly there. Bigger usually means more expensive, but it's fuzzy. It's noisy.
So linear regression is the mathematical task of taking a ruler and trying to draw a single straight line through that cloud of dots that best represents the trend.
The line of best fit. That's the goal.
Right. You want a line that is as close as possible to all the dots at the same time. You want to kind of slice right through the middle of that swarm of bees.
Exactly. But this is where the machine part of machine learning comes in. If I asked you to draw that line, you'd just eyeball it. You'd slap a ruler down and go, yeah, that looks about right.
I would, yeah.
But a computer can't eyeball it. It doesn't have eyes. It needs a number. It needs a specific mathematical way to measure if its line is good or if it's trash.
It needs a score.
It needs a score.
Yeah.
And this introduces one of the most important concepts in all of AI, the cost function, or sometimes it's called the loss function.
I like loss function. It sounds like a penalty. You know, like you're losing points in a video game for being wrong.
It is exactly that. Think of it like a game of golf. You want the lowest score possible.
Yeah.
In machine learning, the score is the error, the amount of wrongness. The higher the error, the worse your model is.
So how do we calculate this error? This is where that acronym came up in the sources, RMSE, root mean squared error. They spent a lot of time on this, and I want to unpack it because it's not just jargon, it's the actual logic of how the machine thinks.
Let's break it down. It sounds way more complicated than it is.
Yeah.
So you draw a line, any line. Now look at one specific house from your data. The actual price was, say, $500,000. That's the dot on the graph.
Okay.
But your line, your ruler, predicted that a house of that size would be $450,000.
Okay, so I'm off by $50,000. That's my error for that one dot.
Right. That's the residual, the difference. Now imagine you do that for every single one of the 1,000 houses in the data set. Some of your predictions are going to be too high, some are going to be too low.
And if you just added up all those errors, the positives and the negatives might cancel each other out.
They would.
So if I'm over by 50K on one house and under by 50K on the next, my average error looks like 0. I think I have a perfect model, but actually I'm dead wrong on both houses.
Exactly. It's a disaster. It gives you a false sense of confidence.
Yeah.
So to fix that, we square the errors. That's the S in RMSE.
We square them. So negative 50,000 times negative 50,000 becomes a huge positive number.
A huge positive number. Squaring does two really important things. One, it gets rid of the negatives, so every error, big or small, up or down, counts against you. And two, this is crucial. It punishes big mistakes way more heavily than small ones.
Because the square of a big number is a huge number.
Yes. If you're off by $1, the square is 1. Fine. If you're off by $10, the square is 100. If you're off by 1,000, the square is 1,000,000. Being off by a little bit is okay. Being off by a lot is mathematically unacceptable to the algorithm. It hates outliers.
I see. So you square all the errors, you take the average of those squares, that's the mean, and then you take the square root at the end just to bring the number back to normal dollars instead of square dollars.
And that is RMSE, root mean squared error. It's the standard ruler we use to measure wrongness in regression.
So the algorithm is basically playing a game of hot or cold. It draws a completely random line to start. It calculates the RMSE score, which is probably terrible.
Probably huge, yes.
And then what?
Then it nudges the line, just a tiny bit. It tilts the slope, what we can call the weight, or W dollars in the formula a little. It moves the starting point, the bias, or $2 up or down a little. Then it checks the score again. Did the error go down?
Woof. Yes, great. Keep moving that way. If no, whoops, move back.
Precisely. It repeats this process thousands, sometimes millions of times in a split second. It just wiggles the line, checking the score over and over until it settles into the absolute lowest possible error it can find. That valley of low error is the solution. It has fit the model. It has learned the function.
And once it has that line, that simple Lie-X plus Bayek equation from 8th grade math, we can finally use it. I can tell the computer, hey, I have a house that is 3,000 square feet and it hasn't been built yet. What's it worth?
And the computer just looks at its line, finds 3,000 on the x-axis, goes up to the line and says, based on the pattern of the past, that house will likely sell for $650,000. It predicts the future.
It's elegant, it's powerful, but life isn't always a straight line, is it?
No. And that is the big glaring limitation of linear regression. It assumes the world is simple. It assumes that if x goes up, y goes up or down at a perfectly constant rate.
The source material gave a great example of this, which was crop yields.
Right. Imagine you're a farmer and you're trying to predict how much corn you'll grow based on how much rain falls.
Okay, so my logic would be 0 rain means 0 corn. A little bit of rain means some corn. More rain means more corn. That sounds like a straight line going up.
It does, to a point.
Yeah.
But what happens if you have a flood? What happens if you get too much rain?
The crop drowns. The yield goes back down to 0.
Exactly. So the graph of your yield goes up, it reaches a peak at the perfect amount of rainfall, and then it curves back down. It's a rainbow shape, a parabola.
And if you try to force a straight ruler through a rainbow shape,
You are going to be wrong almost everywhere. You'll be wrong at the start, you'll be wrong at the peak, and you'll be wrong at the end. Your RMSE will be massive. The model will be useless.
so what's the fix for that?
That's where you'd use something like polynomial regression. It's a slightly more complex model that allows the line to curve. It just adds an sextillo term to the equation, which is what creates the curve. But the underlying logic, the goal of minimizing the error, of fitting the points, that remains exactly the same. It's still just trying to hug the data as closely as possible.
Okay, so that's regression. That's predicting a number, a price, a temperature, a stock value. But a lot of the time we don't want a number. We want a choice. We want a label.
A category.
Right. We want to know, is this email spam or not spam? Is this tumor benign or malignant? Is this customer going to turn or stay?
Now we are entering the world of classification, and this requires a totally different kind of thinking. It's not about drawing lines through clouds anymore. It's about creating rules. And the undisputed king of rule-based learning is the decision tree.
I absolutely loved the analogy in the lecture for this. It's the animal guessing game.
It's something we've all played as kids, right? I'm thinking of an animal. You have to guess what it is, but you can only ask yes or no questions. What is the first question you would ask?
I'd probably ask something broad, like, does it live on land?
Okay. Why that question?
Yeah.
Why not just jump in and ask, is it a zebra?
Because if I guess zebra I have a 99.9% chance of being wrong. I'm just completely wasting my question. But if I ask, does it live on land? I can eliminate like half the animals on Earth in one single go.
Exactly. You're trying to split the data into the purest possible groups. If I say no, it doesn't live on land, you've immediately thrown away dogs, cats, elephants, giraffes, all of them. You're left with fish, whales, sharks. You have massively reduced the uncertainty.
And then my next question is based on that. Okay, does it have gills?
And you just keep going. Step by step, branch by branch, you narrow it down until you're left with just one possible answer. That is a decision tree.
But here's the thing that fascinates me. As a human, I know that does it live on land is a good high-level question. I have intuition. A computer doesn't know what a leg is. It doesn't know what land is. It just has a spreadsheet full of numbers and labels.
Right.
So how does the machine decide which question to ask first? How does it know what a good question is?
That is the clever bit. It uses a mathematical metric, most commonly it's called entropy, or sometimes you'll see the Gini index, which is very similar in concept.
Entropy.
Yeah.
That sounds like physics, like disorder and chaos.
It's very, very similar. Imagine a bucket full of balls, half are red, half are blue. That bucket is completely impure. It has high entropy. It's a mess. If you stick your hand in, you have no idea what color you're going to pull out. It's 50-50.
Okay, maximum chaos.
Maximum chaos. The computer's goal is to reduce that chaos. So it looks at all the features in the spreadsheet. Maybe one column is size and another is weight. It tries to split. It says, what if I ask the question, is the ball heavier than 5 pounds? And I separate all the heavy balls from the light balls.
And then it checks the results of that split.
Right. It looks in the 2 new buckets. If the heavy bucket is still a 50-50 mix of red and blue, that was a useless question. It didn't reduce the entropy at all. But if the heavy bucket is now 95% red balls and the light bucket is 95% blue balls,
Bingo, that's a great question.
that is a high information split. You've created order from chaos.
So the computer just brute forces this. It tries every possible question on every feature, calculates how much each one cleans up the mess, and then it picks the absolute best one.
Precisely. It greedily hunts for the question that gives the biggest reduction in uncertainty. It does this at the very top. We call that the root node. And then it does it again for each new branch and again until it can't split anymore.
Until it gets to the leaf node.
The leaf node. That's the final answer. That's the bucket. That's all one color.
Got it.
Where it says it's a zebra.
This sounds perfect. It's logical. It's interpretable. You can literally print it out and follow the logic. It works like our own brains. But the lecture notes highlight this massive, massive trap here, a trap that they say ruins more machine learning models than anything else.
Oh, yeah.
The villain of our story, overfitting.
Overfitting.
Yeah.
The cardinal sin of data science.
They used a great analogy about students taking a math exam. I want to kind of role play this a bit because it really clicked for me.
Let's do it. It's a great one.
Okay, so I'm student A. I really, really want to get 100% on this test. So I take the textbook and I memorize it. I memorize every single practice problem. I know that on page 5, question 3, the answer is 7. I know that on page 10, question 4, the answer is 42. I have perfect recall.
You have 100% accuracy in the training data. You are a genius. You've aced all the homework.
I feel like a genius. But then I walk into the real exam, and the first question is, what is 5 plus 5? And I just panic, because in the book, the question was 5 plus 4. I've never seen 5 plus 5 before. It's new. I don't know the answer.
And you fail miserably. That is overfitting. You memorize the noise and the specific examples in the training data, but you didn't learn the underlying pattern. You didn't learn how to add. You just learned the history of addition problems that you were shown.
Now contrast that with student B.
Student B didn't memorize a single specific answer from the textbook. Student B focused on learning the concept of addition. They learned the rule, the pattern, that putting two numbers together makes a bigger number.
Right.
So when they see 5 plus 5, even though they've never seen that exact combination before, they can derive the answer. They can generalize their knowledge to a new, unseen problem.
Student B generalizes, student A overfits.
A good machine learning model must be student B. It needs to find the rule, not memorize the data.
So what does an overfit decision tree actually look like in practice?
It looks like a tree that goes on forever. It's way too deep and complex. Imagine playing 20 questions, but you're allowed to ask 5,000 questions. You would eventually end up asking these absurdly specific questions like, is the animal named Bob? Does it have a tiny scar on its left knee? And was it born on a Tuesday?
You're creating a rule that only applies to one specific animal in the history of the world that happened to be in your training data.
Exactly. You are drawing these crazy, jagged, complex boundaries around every single outlier in your data. If you let your tree grow to its maximum possible depth, it will capture all the noise. It will get 100% on the training data, guaranteed. But the moment you show it real-world data, what we call the test set, it just crashes and burns. Its performance is terrible.
So how do we stop the student from memorizing the textbook? How do we stop the tree from growing down to the center of the earth?
We prune the tree. It's a great term. We set limits. We basically step in and tell the algorithm, look, you're only allowed to ask 5 questions deep. That's it. Or we say, you cannot create a leaf node, a final answer, with less than 10 samples in it.
We force it to stay simple. We force it to be more general.
We force it to look for broader patterns, not tiny little quirks in the data. We have to accept a slightly lower score on the practice test, the training data, in exchange for getting a much, much better score on the real exam, the testing data.
And this process of finding the right limit, deciding whether the depth should be 5 or 10 or 20, that's called hyperparameter tuning, right?
Correct. The next step is a hyperparameter. It's a setting, a knob on the machine itself that we, the humans, have to set. It's not something the machine learns from the data.
The sources mentioned a tool called Optuna here, which sounded pretty cool.
Optuna is fantastic. Imagine you have a bunch of these knobs and dials on your machine learning Nginx depth, minimum samples, and so on. You could sit there all day and just twist them randomly to see what works best.
Yeah, that sounds tedious.
It is. Or you could use Optuna. It's an algorithm that intelligently tunes your algorithm. It methodically searches for the Goldilocks zone, the combination of settings that's not too simple, which is underfitting, and not too complex, which is overfitting. It finds what's just right.
It's robots fixing robots. I love it. Now, before we move on to the really advanced stuff, the forests and the ensembles, we need to take a quick but really important detour into the workshop.
The data workshop, yes.
Because the lecture emphasized something heavily. Garbage in, garbage out. You can't cook a Michelin star meal with rotten ingredients, and you can't build a good model with bad data.
Absolutely. This is probably 80% of the actual job of a data scientist. In the real world, data is never clean. It's messy, it's broken, it has typos, it's inconsistent. Data processing is the unglamorous but absolutely essential part of the job.
In the source material, they spend a lot of time on pandas and NumPy. For our listeners, these are not, in fact, cute bears.
No, sadly. They are Python libraries. Think of pandas as, like, Excel on steroids. It's a tool that allows you to load and manipulate massive tables of data millions, even billions of rows in milliseconds. It's the standard toolkit for anyone working with data,
And one of the biggest headaches they discussed was the NaN problem.
the dreaded NaN, which stands for not a number.
It sounds like a philosophical problem. When is a number not a number?
It happens all the time in real data. A sensor fails for a second, a user skips a question on a survey form, you end up with a hole, a blank cell in your spreadsheet, and most machine learning algorithms just cannot handle holes. If you try to feed a linear regression model a NaN, it chokes. It just throws an error and the whole program crashes.
So what do you do? I mean, do you just throw away that entire row of data?
You can. That's one strategy. It's called dropna. If a row has a missing value, just delete it. But that can be really dangerous.
Yeah.
What if 50% of your rows have one tiny missing value in some unimportant column? If you drop them all, you've just lost half your data. You've thrown away a huge amount of valuable information.
So the alternative is, what, filling it in? You fake it till you make it.
It's called imputation. And yeah, that's basically what it is. A common strategy is to fill the hole with the average value of that entire column, or the median value, which is often safer. It's an educated guess.
So it's like saying, I don't know the exact age of this specific person, but the average age of everyone in my data set is 35, so I'll just put 35 in the blank space so the math doesn't break.
Exactly. It keeps the data structure intact, it lets the algorithm run, and it does so without throwing away all the other valuable information in that row. But you have to be careful. If you have too many missing values and you fill them all with the average, you create this fake reality where a huge portion of your population is exactly average, which can skew your results.
Another thing that really stood out in this workshop section was handling dates and times. To a computer, May 18th, 2024 is just a string of text. It's just letters and numbers. It doesn't know that May comes after April. It doesn't know that Sunday is a weekend.
Right. If you feed raw dates as text into a regression model, it treats them like random words. May is no different from apple or banana. It's useless. You have to convert them. You have to do what we call feature engineering.
Feature engineer, that's a cool term.
It just means extracting meaningful numbers from raw data. So from a date, you might pull out the month as a number from 1 to 12. You pull out the day of the week as a number from 1 to 7. Now the machine can see patterns. It can learn things like sales always go up on day 7, or temperature always drops in month 12.
The lecture had a really specific example about chill water supply temperature in a building.
Yes, looking at a 24-hour cycle. To predict temperature, the machine needs to understand time of day as a continuous cycle. It needs to know that 23.00, which is 11 p.m., is mathematically very close to 00.00 midnight.
Right, because 1 hour passes and it wraps around. But if you just give it the numbers 0 through 23, the computer thinks 0 and 23 are the farthest apart they could possibly be.
Exactly, because 23 is a big number and 0 is a small number, so you have to transform the data to match the reality of a clock face. Often we use trigonometry sine and cosine transformations to map the time onto a circle, which makes it cyclical.
Now, I want to talk about one visual concept from this section that I found really, really helpful, the mesh grid. Because up until now, we've been talking about all this invisible math, but the mesh grid lets us actually see what the computer is thinking.
A mesh grid is like mapping a terrain. It's a visualization tool. Suppose you have a classifier that predicts if a spot on a map is safe or dangerous. You have some real data points scattered around, some safe, some dangerous, but you want to see the border, the exact line where the model thinks safe turns into dangerous.
Okay.
So you create a grid. Imagine laying a piece of digital graph paper over the entire map, and at every single intersection of the grid lines, let's say you have a 50 by 50 grid that's 2,500 points, you ask the model to make a prediction, even if there's no real data there.
You force it to predict on empty space.
Right. You ask it, if there were a data point right here, what would you classify it as? And for each of those 2,500 points, you color the dot. Maybe blue for safe, red for dangerous.
And when you do that 2,500 times, you get a picture.
You get a picture, you see a solid region of blue and a solid region of red, and most importantly, you see the line where they meet. That is the decision boundary.
It's like painting by numbers to reveal the hidden logic of the machine.
Exactly. And it's an incredible debugging tool. It helps us humans trust the black box. We can see where it's drawing the line. We can see if the boundary is a nice, simple, straight line, which you'd get from a linear model, or if it's a crazy, jagged, complex shape.
Which would be a sign of overfitting.
A dead giveaway. If the boundary looks like a jigsaw puzzle piece, it's swerving around trying to grab one single red dot inside a sea of blue, you know your model has overfit. You know it has memorized the noise.
Okay, so we've got our data cleaned, we filled in the holes, we've converted our dates, we understand lines, and we understand trees. Now, we scale up, we get to the powerhouse section of the material, the strength in numbers idea.
Ensemble methods.
The core idea here, which I love, is that a bunch of average or even weak learners is better than one supposed genius learner.
Or, to be a bit more precise, a bunch of learners who all make different mistakes are better than one learner. The idea is that if one model makes a mistake on the left side and another model makes a mistake on the right side, when you average their opinions, the mistakes tend to cancel each other out.
This leads us to the first technique, which is bagging, which apparently stands for bootstrap aggregation. Let's unpack bootstrap first, because the math here is really counterintuitive but super cool.
This is a fascinating statistical trick.
Sure.
Suppose you have a data set of 1,000 items, and you want to train 100 different decision trees. Now, if you give all 100 trees the exact same 1,000 items, what happens?
Well, they're deterministic, so they all learn the exact same thing. They all become identical trees.
And 100 identical trees are no better than just one tree. It's redundant, you need variety, you need your models to have different perspectives, different experiences.
So you use bootstrapping to create that variety.
Exactly. You create a new, slightly different data set for each of your 100 trees, and you do it by picking randomly from the original bag of 1,000 items. But, and this is the absolute key, you pick with replacement.
Meaning if I pick item number 5 out of the bag, I write it down for my new data set, but then I put it back in the bag. So I might pick it again on my next draw.
Exactly. You might pick item #5 3 times, and by chance, you might never pick item #8 at all.
The lecture mentioned a very specific rule here, the 63% rule.
Yes. It's a statistical certainty that emerges from this process. When you do this, when you draw n items from a bag of n items with replacement, each new bootstrap bag will contain, on average, only about 62 to 63% of the unique original data.
That's wild to me. So nearly a third of the original data is just left out of each bag, on average.
Yes. And the remaining 37 or 38% of the bag is just duplicates of the items that were selected.
And this is a good thing. It feels like we're losing information.
It's a great thing, because now every single one of your 100 trees sees a slightly different version of reality. Tree A sees lots of examples of X. Tree B sees lots of examples of Y. They develop different perspectives. They become specialized in different parts of the data. They make different kinds of mistakes.
And then you aggregate them. That's the second part of bagging.
You aggregate them, you let them all make a prediction, and then you combine the results. If it's a classification problem like yes, no, they vote. The majority opinion wins. If it's a regression problem where you're predicting a number, you just take the average of all their predictions.
And when you do this with decision trees specifically, when you have 100 or 1,000 trees all trained on different bootstrap data bags, you get
A random forest.
the random forest. It sounds so poetic, but it's one of the most robust, powerful, and widely used algorithms in the entire industry.
It works so well because it directly neutralizes the biggest weakness of the decision tree. Remember how we said a single deep decision tree tends to overfit? It memorizes the noise.
Right. The student who memorizes the textbook typos and all.
Well, imagine you have 100 of those students. But each student only got to memorize a different, randomly selected 63% of the textbook. And some students saw certain pages multiple times and other pages not at all.
Okay.
Now, when you ask them a question from the real exam, student A might have a crazy wrong answer because they happened to memorize a typo on page 50. But the other 99 students, most of them never even saw page 50. Their knowledge isn't corrupted by that specific piece of noise.
So the group just overrules the one individual's error.
The group's wisdom cancels out the individual's noise. The signal remains. It smooths over the jagged, overfit boundaries of any single tree.
I love that. It's like one person might be biased or have a bad take, but a room full of people from diverse backgrounds will usually come to a fairer, more balanced conclusion.
That is the exact philosophy behind it. And random forests have this amazing superpower that was mentioned in the source material. Feature importance.
Oh, right. This is where the model can actually tell you why it made the decision it did.
Yes. A lot of powerful models, like a big neural network, are often a complete black box. You feed it data, it spits out an answer, and you have absolutely no idea why. But a random forest can look at all of its 100 or 1,000 trees and say, hey, I noticed that every time we use column A to split the data, we got a huge reduction in entropy. It was a really useful question to ask. But column B, It was almost useless. It never really helped us.
The example given was the Pima Indians diabetes dataset.
Right. The model looked at a number of medical measurements from patients and predicted whether or not they had diabetes. After training, the researchers could ask the random forest, okay, which of these measurements were most important for your decision?
And what did it say?
It explicitly told them glucose level and BMI were by far the most important predictors. Meanwhile, something like skin thickness, which was also in the data, turned out to be almost irrelevant. It was at the bottom of the list.
That is so incredibly valuable. It's not just a prediction machine at that point. It's a discovery machine. It helps the doctors understand the disease better.
Exactly. It validates the existing medical science. I mean, if the model had come back and said skin thickness was the most important thing, doctors would be very, very skeptical. They'd think the model was broken or had found some weird statistical fluke. But seeing glucose at the top builds trust. It means the model is learning the actual biology, not just a random correlation.
So we've talked about bagging, which is running the same algorithm, like a decision tree, on many different versions of the data. But the lecture went into one final, even more democratic concept, the voting classifier.
The Council of Algorithm.
The Council of Algorithms. I like that a lot better. This is where we don't just use 100 trees. We use everything we've got in the toolbox.
Right. Why limit yourself to one type of model? The world is complex. Let's train a logistic regression model, which is good at finding linear boundaries. Let's train a decision tree, which is good at creating boxy, rule-based boundaries. And let's train a support vector machine, or an SVM, which is another type of classifier that's good at finding complex, curved boundaries.
And these algorithms all think in fundamentally different ways. They have, like, different mathematical brains.
They do. So
Yeah.
you give the same patient data to all three of them. The logistic regression model looks at it and says, based on my linear worldview, I think the tumor is benign. The decision tree looks and says, based on my rules, I think it's malignant. The SVM says, based on my geometric analysis, I also think it's benign.
And since it's a vote,
2 against 1. The final ensemble prediction is benign.
it's literally like getting a second and third medical opinion before you decide to go into surgery.
It minimizes the risk of one specific algorithm having a blind spot for that particular type of data point. Maybe the true boundary was a straight line, so the decision tree struggled, but the logistic regression model nailed it. By combining them, you get the best of all worlds.
Now, there was a really important nuance here that they discussed between hard voting and soft voting.
This is a critical distinction.
Yeah.
Hard voting is just what we described. It's just counting hands. I vote yes, you vote no. It's binary. Each model gets one vote, and majority wins.
Okay, simple enough.
Soft voting is much more nuanced and almost always better. It looks at the confidence of each vote.
The confidence score, the probability.
Right. Let's imagine the famous iris flower data set, which is the Hello World data set for classification. You have measurements of flower petals, and you have to guess the species. Is it Setosa, versicolor, or virginica?
Okay.
Suppose algorithm A looks at a flower and says, I predict it's a Setosa. But if you look under the hood at its probability output, it's only 51% sure. It's basically guessing. It's a coin flip.
It has very low confidence.
Very low. But algorithm B looks at the exact same flower and says, I predict it's a versicolor. And it is 99% certain. It is absolutely screaming that it's a versicolor.
In a hard vote, those are just one vote versus one vote. It's a tie. The third model would break it.
Exactly. It ignores the nuance. It treats a 51% guess and a 99% certainty as equally valid votes. But in soft voting, the system looks at the probabilities. It averages the confidence scores. It sees that 99% certainty and weighs it much, much heavier than the 51% guess. So the final decision would almost certainly swing towards versicolor.
It listens to the actual expert in the room, not just the loudest voice or the first hand up.
It effectively gives more voting power to the model that is more confident in its prediction for a specific data point. It yields better, more stable results almost every time because it captures that crucial nuance of certainty.
Wow, we have covered so much ground here. We started with drawing a simple straight line through house prices linear regression.
The very basic.
Then we evolved to building these logic trees to guess animals, and we immediately learned how those trees can cheat by just memorizing the textbook, which is overfitting.
But we went into the data workshop and learned how to be a good mechanic, how to fix our messy, broken data with imputation and date conversion. We even learned how to visualize the invisible decision boundaries with mesh grids.
And finally, we scaled all the way up. We built a whole forest of trees and then a whole council of diverse algorithms to make better, more robust, more reliable decisions.
It really highlights the evolution of the field, doesn't it? We started with simple statistics from 100 years ago and moved toward these complex, layered logical systems that, in a way, mimic how we organize our own societies, with voting and committees and leveraging diverse perspectives.
It does make you wonder, though. We mentioned AutoML briefly, automatic machine learning. The lecture touched on how these modern tools are getting good enough to just pick the best model for you. They do the whole process.
It is the next frontier, without a doubt.
So here's my final provocative thought for you to chew on. If we have these tools, these AutoML platforms, that can take a data set, clean it automatically, try linear regression, try random forests, try voting classifiers, tune all the hyperparameters with something like Optuna, and just spit out the best possible result, what happens to the data scientist?
It's a great and slightly terrifying question for people in the field.
Are we moving to a world where the human is just the supplier of clean data, where our only job is to shovel the coal into the furnace and the machine decides how to burn it to get the most power? Or is there still an art to this science that a council of algorithms can never, ever replace?
I think. I think as long as we need to understand the why, like in the diabetes example, why glucose matters more than skin thickness, I think humans are essential. The need for interpretability, for storytelling, for trust, that's a human role. But the how, the mechanical process of finding the best model, the machine is getting very, very good at the how.
Something to think about next time you look at a spreadsheet. It's not just numbers, it's patterns waiting to be found. Thanks for diving deep with us.
Always a pleasure.
See you next time.